We'd like to invite Spectrabotics to the stage.
Good morning. This beautiful park in Boulder, Colorado is hiding a killer. And it's got environmental scientists from Boston to Boulder deeply concerned. It's small to the point where you can't see it with any conventional remote sensing from a standoff distance. And eventually, untreated, it kills the host. It flies on the wind, it migrates. It targets a specific tree. Here's an example of the migration pattern that it's been moving across for the last 20 years. And once again, I find myself on the front lines of trying to understand how it's moving. How do we stop it? I'm Tim Haynie. I'm the CEO and founder of Spectrabotics out of Colorado Springs. And I'm no stranger to the spectral systems that are out and trying to understand the environment or trying to figure out what's going on. Years ago, I used to work with MODIS and Astrodata to help fight fires in Colorado. And then in the desert, I used Hyperion and ALI and Landsat to look for anomalies. And you haven't lived until you stood in front of your boss and said, could be a milk truck, could be a missile launcher. We don't quite know, but I found an anomaly. So you can imagine how excited we were when we were looking at this EAB problem. And then we realized that we've got access to drone technologies that can help us put a sensor where we want, when we want, at the altitude we want, to get the resolution we want. And we can do this high fidelity analysis that can give us a much better picture of the extent, or how to find these and how to mitigate it. Who do we tell? So collecting the data was sort of easy. We figured that out. And even though it's a lot of data, there's been a lot of advancements with cloud technologies and high-speed networks, so we can manage what's being collected. And we can process it because there's some great commercial software out there that puts together these images, these stacks of data. But the problem is they weren't built for me. They were built for the commercial market that's looking for mapping. So all this drone data, when it goes through the processing systems, it contorts, it changes the data to the point where now we're suspecting that our analysis is perhaps wrong. It's trying to take a 2D image and wrap it around 3D objects, because height is one of those byproducts that we can get from photogrammetry when we use this. So right then we were kind of scratching our heads. What do we do next? Well, we sort of went with what we've got. We built our own system to do that. It's still a work in progress. It's very complicated software. But really we got it to the point where, okay, let's take what we've got and let's run it through our analysis systems. And it's conventional, it's commercial software, and let's do some band math on this with stuff that's been well studied, chlorophyll absorption, stress. Let's apply those techniques and see what we learn. And what we found out was, once again, it's not built for us. It's looking pixel by pixel, trying to match what it thinks is an object, grass, tree, sidewalk. And because of the resolution of the data, it's so high that it confuses itself with the angle of the leaf or the glint of a stone in a sidewalk. That throws it off. So now we're worried that we don't have the analytic tools we need to find the EAB. And that wasn't the worst part. The worst part was actually that the customer in this case, the city of Denver, really doesn't need the imagery. They want the insight. And so how do we take that image and turn it into something that's actionable for them? Because it's just a picture at the end of the day. There's a lot more information that needs to go with it. So we had to go back and bring in some new talent. And the two gentlemen that I'd really like to highlight because of their skill sets, one is Eric Shabe, who comes from working with a lot of government systems out there and building really fast processing and cloud services so that we can look at not just this data, but lots of other data, and how do we aggregate that, and how do we store it, and how do we make it searchable. And then the other talented individual is Dan Vaugh. And because academia really isn't kicking out data scientists at the rate we need them, Dan has sort of taken his passion for remote sensing and development and then applied it to the world of physics so we can understand how this light interaction is going on behind the scenes. What is this sensor collecting, and why is it collecting it in that way? And then there was another person we had to bring on, and this is sort of mission specific. So the person who actually brought this problem to us is an arborist with another startup called Arbor Drone, and Dan Staley, who's watching via livecast. He was the one that introduced us to this and said, hey, there's an opportunity here to take these overhead pictures and apply it to the EAB problem. And he really took us through the paces of understanding how complex biological systems represent themselves across the spectrum. But the problem again is, look, it's too much data. We know how to collect it and process it and store it, but when it comes to that analysis part, there's still a human in the loop that's making a qualitative assessment on what it is. I've been down that path and I wasn't comfortable there. So we go to the machines and say, let's introduce some machine learning tools and let's figure out what these relationships are. Let's let the computers tell us what it thinks it is after we've already taught it. And for those of you who don't understand or haven't been exposed much to machine learning, it's basically you give it an input and you tell it what it is. You tell it it's a tree, it's a sidewalk, it's a soccer field. You don't necessarily say, this spectrum represents an oak tree or a blade of grass. You just tell it what it is. And then there are a number of classification programs that can run through it very fast and understand the relationships between all those bands of data. So instead of having to upload lots and lots of pictures of a cat, for example, we can speed that process up by using spectral data because we're looking through the data sets, not simply at a 2D image. So if we go back to the original product that we built, find the ash trees in here. Well, I've told it what an ash tree is, and it still couldn't find it. We've lost that signal in the noise. But after we run it through machine learning, we get a much more refined view. And so now the computer's telling us this is a field. This is a field with a lot of dirt in it. These are different species of trees, although we're still working on how to separate and identify those species. That's a work in progress. We can at least tell trees apart from each other. We can tell artificial stuff from natural objects out there, simply by telling it what it is. So, okay, we've got this machine learning that can kind of give us a macro perspective on it, but is it good enough to find EAB? And the thing about EAB is obviously we're not going to find the bugs themselves, so you're looking for the impact it's having to its host tree. And it's actually stages, so the longer the EAB is in the tree, it progressively gets worse over time. And so here's 3 examples of trees that are in all 3 stages of infestation. So obviously the late stage is early to see. It's the early stage that we're after because there is a point where you can do some intervention and do some treatment so you can save the tree versus having to remove it, which is expensive and impacts lots of other aspects of quality of life. So we can see it. We haven't got to the point now where we can do this with machine learning. That's going to take a lot more study, but at least the indicators are there. But it's not just that data that we're interested in because, like I said, the city of Denver doesn't necessarily want the image of it. They want to know how fast is it moving. They're our customer because they see it in Boulder and they know it's coming in through a corridor down into the city. And that's where they want to catch it before it gets into the urban forest region. So height matters, weather patterns matter, soil composition, tree species that are nearby. All of these impact how that migration occurs. And the list just keeps on growing. What else can we think about that can give us more insight into what's happening? So let's just talk about height for a moment. Why is that important? Well, height is one of these derivative products we get when we do photogrammetry. And it's fairly accurate. It's within 6 inches based on the resolution of the data. And just with height alone, I can start to assign it to a tree, and now I can start to work on refining what species is it based on its shape, its crown density. Or if I'm looking for man-made materials, you know, a roadside and a house shingle look very similar. So how can we distinguish between the two? Well, height can help us do that. And do these AI models work? You know, it worked on the Denver park data, but does it work in an urban setting? And they do at a macro level. We're seeing some relationships there. And then can we scale it? So here's the background image there was imagery taken from an aircraft this year, where we're attempting to take those models we built in Boulder over the test park and applying them to an urban setting, which much more dense, much more cluttered, and a lot bigger. And this is the key, these tools. These tools, when you apply them to data, and you can bring together disparate data that doesn't work well necessarily, you can aggregate this, apply this machine learning, you increase the value of the data as well as the utility of the data. And that's where we're targeting. How do we make these systems more important? So we've got some early revenue customers. We're on a contract with Sporian Microsystems to take their hyperspectral sensor and build a machine learning algorithm for their data analytics. They realized that they can sell more sensors if there's a data service to go with it. The city of Denver we've talked about, we're on our second proof of concept with them from last year and this year, scaling up our studies. And then as well, we've got some precision ag market customers that are very interested in this tree technology or this tree studies that we're doing and applying it to orchards. So this is how we're different. We're that connective tissue. We're that pathway between the sensor market, the data collectors, the people that are able to go out and collect this information, and then the subject matter experts that understand these complex environments, these complex interactions. We sort of connect those two together. We've seen in the past, especially in the drone space with precision agriculture, that the drone pilots can build a product. They can build a very detailed map, and there's great information in there, but when it's passed to the customer, some of that gets lost because they're not exactly attuned to how to interpret it. We've got two beachhead markets we're applying this technology. The first is in orchard management. California being the largest state with 38,000 orchards out there, just a 5% market penetration nets about $4 million through our SaaS model service. And that includes others doing the data collection. We do the processing and analysis and then turn it back as a final product. The future of this is obviously specialty crops. The one we're really interested in is vineyards, because there's already a lot of studies going on in vineyards. A lot of those fields are wired for soil moisture, soil connectivity, air density, moisture, pressure, rainfall. All of that is important to understanding the overall health, not just a relative index of what its health status is. Our other beachhead market is in urban forestry. We've been talking a lot about this, and there's roughly 100 cities with a budget that could pay for a service like this and concerns about their urban forestry strength and management. So a 10% market penetration there yields about $500K, but that's really not the point. The point here is leveraging utility of the data. It's the ability to take the data that we collected to do urban forestry studies and then repurpose that data using the same analytic techniques, the same machine learning tools to say, okay, now we want to go after roadways. We want to find potholes. We want to find frost heave. Or public services. We want to see where trees are encroaching into the power lines so when storms occur, we don't lose power as often. Or even public safety, where we can say, okay, here are all the accidents. Here's how they occur during a significant weather event. How do we understand the correlation so we can make our streets safer? Now, these are our commercial markets, certainly. Precision agriculture, working with smart cities, which is a big growing industry, and there's a lot of Internet of Things applications that are going on that are a little disparate from the imagery world, but there's always a reason to bring them together. There's new things to be learned when we can integrate sensor data with imagery data. They're not that far disconnected. And NASA has many of the same missions, the same concerns. A lot of the environmental science is being conducted from remote sensors either on a rover or in space, have direct applications with what we're doing with the drones. The difference being more or less the resolution difference between the two. So we see a tremendous opportunity to aggregate this data, analyze it, and then visualize it, turn it back around. So the first slide that you saw, some of these boxes were grayed out. We want to take that away. We want to bring all this data together, and let's see what happens when we understand these relationships. Even though there's a coarseness in the resolution, there's still much to be learned in that gap, right? We've got the high resolution with the drone layer. You've got the macro resolution with the satellite layer. There's a big gap in between. How do we exploit that gap? And we believe we can do it through machine learning, through model development, through collaboration, and then put this towards those future systems. So if you've got a rover on Mars, for example, that's got a high-resolution hyperspectral camera that can tell you exactly what's on the ground, how does that correlate with what's in orbit? How can we speed up the process of analyzing large bodies out there with technology that we have today? So our ask is to let's connect. Let's get together with subject matter experts, with topographic experience, with imagery experience, and then let's figure out how do we take all this data that's likely hitting the floor and bring it back up and start to work with it again. And then, of course, we need to continue development on our platform for the commercialization. A lot of it is still hand-entered, and we'd like to repurpose or build a UX UI to go along with that. And with that, I will close and I welcome any and all questions.
I'll take the first one then. You said about space debris. Can you explain a little bit more about how you would impact the space debris issue?
So in my world, data is data. I don't feel like I'm limited to just optical or just radar or just sensor data. It's just ones and zeros. So the problem with space debris is how do you find it and how do you track it? Because they don't necessarily have pings and they're tough to see optically. Where we miss the boat, I think, in space is so many of our tracking systems are siloed. Okay? And the government has some very good systems, but so do other foreign governments, and so do amateur astronomers, and there's ham radio operators that are able to track things from space. So it would be better if we could collect all of that into a system that can rapidly analyze it and look for those variations of change over time with these systems and can sort of point us in the direction where the debris fields are. Or, just give us a better sense of where what we know is through this aggregation of lots of different disparate information sources. And that's what we've worked a little bit with that. Eric Shabe has taken that project specifically for an Air Force customer that's interested in it. I hope that answers your question. That's a tough one to answer, and it really has to do with the aggregation of lots of different data sources to start to understand relationships between bodies we can see and bodies we can't.
Okay, so I'll maybe ask you an easier one, because I know debris is a difficult question. So on precision agriculture, which I have particular interest in, how fast the rendition or latency of your data processing could you do if I had a farm that had an issue that I need to address pretty quickly?
Right. So the question is, how fast can we process this and turn an answer back around to a person on the ground? There are systems out there that can do it almost immediately when they land. There are sensors that have been built from other companies that will fly, and by the time it lands, there's a gross sort of rough estimate of what's going on. And the normal turnaround time, if you were to work it on a workstation right there, is probably about 2 hours, maybe 3 hours. But the problem is, number one, it's one layer, all right? It's chapter one of the entire series because farming is extremely complex. The second problem is it gives you a relative answer, not a definitive answer. So when you're looking at and mostly they give vegetation indices, so we're looking at relative health based on IR reflections that are coming in. It varies from day to day, it varies with sunlight conditions, it's very difficult to pin down at anything quantitative. So it's sort of subjective what we're giving them. And then the third problem is how does the farmer interpret that into something that's actionable? And that's where I think we kind of missed the boat there as well. So what? And we've heard from a lot of orchard growers connected with Colorado Springs or CSU that say, yeah, it's great, but it doesn't jive with what I'm already thinking is the situation on the ground, so there's a disconnect there. And then now what do I do to improve the health or optimize how we do growing? Thank you, great question.
You had an example up of 5% of getting the market in California, specifically in ag tech in your niche, turned into 4 million annual estimation?
Correct.
Yeah. Can you talk a little bit about the margins on that estimation? Like what would the margins be for your company on that?
Very difficult to pin down, and I'll tell you why. We don't do the data collection piece of that, and that's largely the bulk of the cost is in the data collection. That's, people have invested in the hardware to do it and the time and the expertise to go out and do that. We're simply that connective piece, that link that says, okay, give me your data. And for us, the costs is the, to run and manage the cloud services that do a lot of the processing, and then offset the cost of all the UX UI development that had to go into, had to be built to handle that. But there's a component to this that we didn't talk about so much that I'll just hint at, is once you've got this as a SaaS model in place, and once you've got data coming in and you've got people using your system, it gives the potential to build a marketplace for applications. So someone who's a subject matter expert in this particular phenomenon or this particular data set or combining data sets has the opportunity to build something unique, much like an apps market we have for smartphones. So the ability to lend your expertise and then make that available to others opens up a wide range of opportunities One for revenue streams, based on how much value you can create or increase through the use of this application, and then licensing certain technologies for other applications or for other uses outside of precision ag or urban forestry.
Great, and then my other question was regarding your ask. Can you be a little bit more specific about your ask at this moment in time?
So the ask is access to subject matter experts. You know, data science, artificial intelligence, machine learning is really a big black box at the moment. You know, we've got some expertise in there, but there's a lot that we don't know, and there's a lot of people building applications that aren't going through the intellectual rigor, I guess, to ensure that you can repeat those results over time. And so there's a lot of work that needs to be done in developing this and applying the right talent to building out some of these machine learning routines that give us this consistency that we're looking for. And I believe NASA is a great warehouse of expertise, not only with their sensors, but also in areas of environmental science and studies, and of course space science. You know, how can we bring these two together with the data we're already collecting? And we'd like to be there. We'd like to be there with between the subject matter experts that are coming up with the problem and truly understand the problem, and those that are doing the data collection and really don't know what happens after we've received it at the ground station. Does that answer your question?
Kind of. I was also looking for a specific number with regards to your ask, like for the second bullet there on your screen.
Right, let's talk offline about the number, because it really depends on the scope of what we're going after. You know, and you know, quite honestly, the number is used to fund talent that's needed to bring in. You know, really there aren't a lot of hardware costs that need to go into it. That's sort of fixed at the moment, but the talent we need to go after a specific problem is what we would spend that money on. Yes, sir.
Your expertise is in both the computer program and agriculture, but can you go to other areas like geography or geology or other subject areas and use your computer program for that?
So we've identified 6 other market opportunities that this can be applied to. So for example, mining, right? So a lot of the sensors we use in precision agriculture were designed for living systems, but mining and geology is out. Most of those features are in a different part of the spectrum. So we don't have a lot of sensors out there to work with just yet, but there's still a lot to be learned by understanding what can we do with the sensors we've got in the mining applications. Also, search and rescue is another, where we can do wide area searches looking for anomalies that we can immediately determine that there's a lost hiker, for example. Or another is infrastructure. So we've got power companies out there that are very concerned about encroachment of trees into power lines or waterways, things like that we can do some rapid analysis on, say, all right, here's how you optimize your operations to go out and deal with these. Instead of going to every site, go to these first. So there are a number of opportunities, and we don't have to rebuild the system to do that. We're data agnostic, we're process agnostic. Just tell us what you want it to do.
So if they're not going to ask, you've been talking to this, and I'm probably just not fully appreciating it given my background and stuff. If you had asked me, I would think Google, there's some obviously big companies that do something similar. I mean, from a machine learning, data analytics. So help me understand again where your expertise is and what the value added is.
Right, so there are some really heavy hitters in the GIS space, for example, that have been around for a long time and truly understand how to layer in GIS, because a lot of this remote sensing that's being done generates these GIS layers. What they don't do is the integration of other sensor data that doesn't fit well with a GIS system. So for example, like weather data, and we're not talking about satellite images of clouds, or we're talking more about wind information and direction and gusts, humidity, pressure, temperature, how does all that impact, not just where we are right here at this point in time, but where are we going? What's the trend? Where did we come from? What were the anomalies? And that's what the system is built to do. Most of these sensors have a GIS component that makes it easy to explain what's going on with a GIS platform, but the ability to take other sensor data and integrate it with that GIS component, because GIS is sort of the language we can all understand. It's a great way to translate it. But that integration of other sensor information that's been through the machine learning process that says, okay, show me the anomalies, or show me the trends, or show me the correlation between air temperature, pressure, and soil moisture so I know when to water. A GIS system is not going to tell you that. And a sensor manufacturer might tell you what my sensor is reading, but it doesn't tell you how it relates to the sensor sitting next to it that's measuring something differently. But the two are related, trying to describe this very complex environment. So that's what our system does better, I think, than a standard GIS application or even a drone company out there that's able to do remote sensing. It's that integration, that aggregation piece that's data agnostic. Great question. I love that question. I'd love to talk more about that. We've got ideas.
Okay, thank you.
Thank you all. It was a pleasure to be up here.